Welcome. Today we're going to do math. Not so much as pertains to game development as usual, but I hope you'll stick around anyway because the topic today is very interesting. It's enumerative combinatorics, which is really just what it sounds like. It's counting things. It's counting different combinations of things, and that sounds like a really straightforward and simple thing to do, but we'll see that it has a lot of interesting ramifications. So let's get started. And the first question is, what is a function? What is a function? I know that sounds like a really simple question. And why are we talking about functions? I thought it was combinatorics. What's a function have to do with combinatorics? And the answer is that functions are the basis of a lot of things that are done in combinatorics. And so we have to study functions a little bit before we can get to the actual combinatorics part. So I want you to think about that for a moment. What is a function? Probably, if you're a programmer like I am, you have a response that's something like, well, a function is something that takes some input and produces some output. And that's a good answer if you're a programmer, but for a mathematician, it's actually a wrong answer. So let's take a look at what a function actually is. A function f that goes from a set A to a set B. Okay, that means A is a set. It has a lot of things in it. Here are some of the things in this set. And B is a set. It has a lot of things in it, right? And A is called the domain, and B is called the codomain. Well, a function is a relation that maps everything in A to something in B. Here's an example mapping. Okay, and that relation is the function. So mathematically, functions don't do anything. They don't operate on some input, then crunch it together and then spit out an output. They're just pointer. If I'm a function and you tell me 5, then I'll say 2. I'm relating 5 to 2, and it's that relationship that's important with a function. It's not what it does, it's the relationship of when you give me 5, I give you 2. Now this sounds like a pretty minor distinction, like who cares, but it's gonna, like I'm asking you to hang on a little bit because it's gonna be an important distinction a little bit. So let's give some examples of some functions just so that we're all on the same page, okay? The function sine, which you are probably familiar with, takes real numbers to real numbers. The domain is real numbers, and the codomain is real numbers. And I'll write some elements of the domain. Okay, you can have sine of 0. These are just some. There are many more. I've only written 3. And then here are some things in the codomain. Okay. So sine maps 0 to 0. So I'm going to write an arrow from 0 to 0. Okay. In other words, that's like saying sine of 0 is 0. Sine maps pi over 2 to 1. It creates a relationship between pi over 2 in the domain to 1 in the codomain. And pi, it relates back to 0. As you know, sine of pi is 0. Okay? So this sine is a relationship from all real numbers to some other real numbers. Okay, so let's give some examples that a programmer might be familiar with. Chances are you're a programmer if you follow my channel. If not, sorry about that. I'm going to do a few programming examples for a minute. Hopefully you don't get lost if you're not a programmer. So this is a C function, but to avoid ambiguity, because a C function is not always the same thing as a mathematical function, from now on, when I talk about something that you program in C or C++ or Java or any programming language, I'm going to refer to it as a procedure because it's not always a function mathematically. But so let's say this procedure right here, this is a procedure f that takes some input a, okay? The name is lowercase a, and the struct or class or what have you is capital A, and then it returns something that is a b. Well, this actually, so assuming that this procedure doesn't throw any exceptions, or doesn't read from somewhere that like any global variables other than this little a, or doesn't write out to something other than this capital B, or do anything crazy like that. If it's really just a simple function, a simple procedure that reads from A and writes to B, in that case, f is a function, and its domain is anything, any value of A, and its codomain is any value of B. So that's a case where a procedure, like a programming function, is also a mathematical function. So draw a line here. The next example of a function that any programmer is going to know, here it is right here. Okay, this is an array. So what's the codomain of this function? Okay, the codomain is the quote output, and so that's going to be B, and the domain is going to be integers, of course, but specifically which integers? Only the integers that are valid for me to use in this. So it's only the integers from 0 to n minus 1. And this is actually a great function. So this function will take any of these integers and spit you out something in B, some B thing, but it doesn't actually do any work. Notice it doesn't actually do any work like a procedure does. You get this function absolutely for free, right? And the structure of the array does this arrow mapping business for you. So one final example of something that is a mathematical function. Hopefully you are familiar with C++. This is going to be a C++ example. And I'm not going to use A and B anymore because that's making this too obvious. Okay. This is a stud map from string to int. And I'm going to assign a few values here. Let's do hello equals 2. And sailor equals 5. So this also is a function. What's the domain? So here's our function. What's the domain here? It's the quote input, right? And so that's string. But it's actually not all strings, because there's a secret rule about functions that I haven't covered yet. And that is that a function has to map everything on its domain. If we come back up here, notice that everything in the domain, I've drawn an arrow from it. Okay, so the rule of a function is that everything in the domain has to have an arrow coming out of it. And down here, you see that I've only mapped 2 of the strings. So this is not every string possible. It's only the strings that I've actually assigned values to. So I'm going to put a little star here to indicate that my domain is not every possible string, because that's literally infinity strings. And we can't, like, our computer doesn't have enough space to store infinity strings, right? But the codomain is any integer that's able to be represented by int right here. All right. So a stud map is mathematically also a function. Okay. So that's cool. There are a lot of functions that we use in our programming lives that are very common. Now, I want to talk about a specific kind of function, and that's a bijection. A bijection. And don't worry, this is going somewhere. We're gonna do some really cool stuff with this, so just hang with me. You're like, why the hell do I care about bijections? Well, I'm getting there. So a bijection, so let's see. What is a bijection? If you have a function from A to B, and A has these elements, and B has those elements, okay? And then I can have some mapping from A to B like this. And these arrows constitute the function f. A bijection is a function where you can reverse all of the arrows and still have a valid function. Okay? So remember, the rules of a function is that it has to map everything in the domain to something in the codomain. And it can also never map the same thing twice. So for example, no, that was okay actually. Here I've drawn a second arrow coming out of this bottom element right here. That's not allowed. I have two arrows coming out of something on the left. A function's not allowed to do that. Then, it'd be like you have this function right here, and then, both of these are f. It doesn't pass the vertical line test. Like if your graph does like this, it doesn't pass the vertical line test, and so it's not a function. So we're only allowed to have one arrow coming out of each item on the left. So if we erase the arrowheads over here and draw them over here instead, you can see this is still a function because everything on the right still has exactly one arrow coming out of it. Hopefully this is clear which thing these are coming out of. Every item on the right still has exactly one thing coming out of it. So this is still a function. Whereas if I draw another function over here, and I draw my arrows a little bit differently, this goes here, this goes here, this goes here, this goes here. So there's nothing coming to this guy. And there are two things coming to that guy. So if I reverse the arrows and draw them over here instead, now we see there are two arrows coming out of this guy and no arrows coming out of that guy. That's not a valid function anymore. It was a valid function before when I had the arrows on the right because there's only one arrow going into or out of anything in the domain. But once I reverse the arrows, it's no longer a valid function. So this is not a bijection. This is not a bijection because there are two. When I reverse the arrows, there are two arrows coming out of this guy and no arrows coming out of that guy. So this is not a bijection. Okay. So let's see my notes here. So if you can reverse the arrows, like I can reverse the arrows in this guy on the left, then I have a bijection. And if I do so, then let's see here. So let's say I have 4 guys here and 4 guys here. This is an interesting point right here. If you have a bijection, I'm going to draw some random bijection. This one goes here, this one goes here, and this one goes there. Okay? This is a bijection. And you can see that if I have a bijection, then I have 4 dots on the left, and 4 arrows in the middle, and 4 dots on the right. And every dot has 1 arrow associated with it. So if you have a bijection, then you have to have the same number of dots on the left as you have arrows as you have dots on the right. And in this case, the size of your elements on the left is equal to the size of your elements on the right. If your set is finite. This doesn't apply if your set is infinite. But if your set is a finite set and you have a bijection between your two sets, then the two sets have to be the same size. You can see that if I add another element here on the right, then there's not going to, like, I'm not going to be able to put an arrow to it. I don't have enough arrows coming from things on the left. And if I add something on the left, then I'm going to have too many arrows going to something on the right. So there's no way I can have a bijection if there are a different number of things on the left as things on the right. Okay? So reversing these arrows like that, when I reverse the arrows, there's a name for that. It's called the inverse function. You may have guessed that by now. And So the inverse function, I'll write that down. Inverse function. And when there is a bijection between two sets, when there exists a bijection between two sets, like what we've shown right here, then there's a word for that. Those two sets are called isomorphic. Isomorphic. So in this case, there exists a bijection between the set A and the set B, and so you can say that set A and B are isomorphic. So cool. So that is the end of the set theory preliminaries that we have to cover. Now, let's get started on some enumerative combinatorics. So now I would like to define a set of objects. I'm going to call it Gn. And these are grid walks not crossing the diagonal. And I'll show you what that means. So I have a grid with a diagonal. All right. And I start here and I end here. And let's see, let's get a different color here, yellow. And I'm allowed to go right and up, right, up. I'm not allowed to go left or down. And I'm not allowed to cross this diagonal line. So these are grid walks of an n by n grid. In this case, n is 5. Okay, so this is a 5 by 5 grid, and I'm not crossing the diagonal, and I'm only going right and up. So the question is, let's keep track over here of, for any value n, what is the size of Gn? So for example, if n is 3 and I have a 3 by 3 grid, how many ways are there to traverse a 3 by 3 grid? So that's what we're asking. And let's start with n equals 0. If n equals 0, let's see. This is what my grid looks like. It's a 0 by 0 grid. There's nothing in it. The start and the end are the same location. How many ways are there to do this? Well, the answer might be surprising to you. It is in fact 1. There's one way to do it. There it is. It's done. Okay. Now let's look at 1. A 1 by 1 grid. Let's see how many ways are there to do that. Okay. Here I've just drawn a 1 by 1 grid. Here's the start. Here's the end. We can see that there's exactly one way to traverse it. You go right and then up. So there's 1. So hopefully you're getting the idea now. Let's draw a 2 by 2 grid. See if we can get some more interesting numbers here. Okay, a 2 by 2 grid. And there are 2 ways to do this. You can go right. Let's get a different color than this one. You can go right, up, or you can go right, up, up. So if n is 2, there are 2 ways to traverse it. So you're getting bored. Don't worry, it will get more interesting. You're thinking, well, these are Fibonacci numbers, obviously. Well, no, they're not Fibonacci numbers. All right. So a 3 by 3 grid. How many ways are there to traverse the 3 by 3 grid? We can go right, up, up. I'm not going to draw the grid for all of these. It'll take too long. You can go right, up, up. You can go right, up. Nope, sorry, you cannot cross the diagonal. So you can go right, up, up. You can go right, up, up. And you can go right, up, up. So I don't think I forgot any. So that makes 5 ways of traversing a 3 by 3 grid without crossing the diagonal. Hopefully you guys get the idea by now. So I'm just going to fill in some more numbers here. When you have a 4 by 4 grid, there are 14 ways. When you have a 5 by 5 grid, there are 42 ways. When you have an n by n grid, these numbers are the Catalan numbers. And there is in fact a closed form of the Catalan numbers. Let's see. Cn equals 1 over n plus 1 times 2n choose n. Well, I'm not going to prove that right now. You don't even know how to have to know what it means. Just believe me that, you know, there is a way to find these numbers. They're special numbers. George Catalan developed them. So that's it. That's Gn. That's grid walks of an n by n grid. So let's move on to the next mathematical set that we're going to think about. And that is Pn, which is valid formations of n open and n closed parentheses. There's a point to all this. Trust me. Okay? So let's say I have 3 open and 3 closed parentheses. I can do maybe something like that. Okay, 1, 2, 3 open and 1, 2, 3 closed parentheses. I can even go crazy. I say something like that. Okay, but my rule is that I must never write a closed parenthesis before an open parenthesis. That wouldn't be valid. All right, so let's see how many. Let's count again. We're gonna write n and the size of Pn. So when n is 0, how many valid ways are there to form with 0 open and 0 closed parentheses to satisfy all these rules? The answer is 1. I drew it in this box. There are no open and no closed. It satisfies all the rules. You're done. So next, when you have 1 open and 1 closed parentheses, that's it. That's the only way to do it. Okay, next, let's go to another color. When you have 2 open and 2 closed parentheses, you can do open, open, close, close, and you can do open, close, open, close. That's it. Those are the only 2 ways of doing it. So this still looks pretty boring so far. Let's see what is going on with 3. So with 3, you can do, let's see, open, close, open, close, open, close. You can do open, open, close, close, open, close. You can do open, close, open, open, close, close. You can do open, 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 close, close, close. Or you can do open, 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 close. No, wait. I already did that one. Open, open, close, open, close, close. Yep, that's it. Those are all the ways. Don't think I missed any. All right. So there are 5 ways of doing this. So these are starting to look familiar. I wonder if they're also Catalan numbers. Here's a spoiler alert. So, but you don't have to take my word for this one, because we're going to prove it. We're going to prove that the number of open, closed, n open, n closed parentheses, the number of ways, to do any of these combinations is the same as the number of grid walks. All right. So hopefully by this point you've seen that there's a lot in common with grid walks, between grid walks and parentheses. So for example, I'm gonna draw a grid walk right here. Well, let's draw a grid first. Let's draw a nice complicated grid. There we go. Nice complicated grid. And then I'll draw a walk. So we went right, 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 up, right, up, right, up. Now I'm just gonna go ahead and write a, so that's, let's see, n equals 6 in this case. We have a 6 by 6 grid. I'm just going to go ahead and write a 6 open, 6 closed parenthesis combination that corresponds to this grid right here. Okay, so let's do it. I'm going to write open, 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 close, open, close, close, open, close, open, close, close. So hopefully you see how that worked. Every time I have an open here, every time I go right here, it corresponds to an open. And every time I go up, it corresponds to a close. It's the same thing as saying right, 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 up, right. Did I do this right? Oh my god, I didn't. Right, 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 up, right, 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 up, right, up, up. No, I did it right. Right, up, up. So you see there's kind of a correspondence between grid walks and open close parentheses. And we've shown that we've actually drawn an arrow between this grid walk and that parenthesis. This arrow is actually a general arrow. We can draw this arrow between any grid walk, okay? And we're going to be given a valid parenthesis configuration. So what we've done is we've defined a function. We've related any grid walk to a corresponding parenthesis configuration. Okay? So I'm going to call that function phi. Phi is a function that goes from n by n grid walks to n open, n close parentheses. And that's the function. The function is when the grid walk goes right, make an open parenthesis, and when the grid walk goes up, make a closed parenthesis. So we're going to show that this is a bijection. And to do that, we're going to reverse the arrow. Okay? We're going to reverse all these arrows, and we're going to show that it's still a function at that point. So if you start with parentheses, this is the question. If you start with parentheses, can you get a valid grid walk? Will you get the same grid walk as you started with before you reverse the arrow? And the answer is yes, because you see an open parenthesis and you draw a right. You go right in your grid walk. You see a closed parenthesis and you go up in your grid walk. Hopefully this is clear that these two things have this bijection. Hopefully this bijection is clear. So if you've done this, then because of what we said before, we've shown that the size of Gn is equal to the size of Pn, and Gn and Pn are isomorphic. So cool. We've shown Gn and Pn are isomorphic. So that means that the number of ways to cross an n by n grid without crossing the diagonal is this. So sorry. Let me back up. The number of ways to cross a 1,000 by 1,000 grid without crossing the diagonal is the same as the number of ways to the number of arrangements of 1,000 open and 1,000 closed parentheses. It's the same number. It's some huge number. Who knows what it is? Gigantic number, but we've proven that it is the same number. Okay, let's look at another set that's interesting. We're going to look at the set Mn of mountain ranges. So this one's going to be fun. Okay, we have a horizon here, and then we have some mountains, and every mountainside can either go up or down, but you always go one to the right. So I go right and up, and then I go right and up, see, and then I go down and up, and then right and up, and then right and up, and then down and up, and then down and up, and then right and up, and then down and up, and then down, right and down, and then right and up, and then right and up, and then right and down, and then right and down. Okay? So my rule is that I can go up right or down right, but I can never go below the horizontal line, the horizon. And it looks like a mountain range from the side, right? It's a mountain range. So it's called Mn. Okay, so let's do this counting thing again because it's really fun. We're going to look for each n, what is the size of Mn? For 0, you got it. There's one way to do it. There it is. Boring. For a 1 up and 1 down mountain range, that's it. That's the only way to do it. So if you have 1 upside and 1 downside, there's only one way of doing it. let's say you can go up twice and down twice. Well, so now you can go up, up, down, down, or you can go up, down, up, down. So if n is 2, and you have 2 ups and 2 downs, then there are 2 ways of doing it. You're probably seeing a pattern by now. Let's see what happens when n is 3. You can go, well, let's not do that. I won't draw the horizon anymore. You can go up, down, up, down, up, down. You can go up, up, down, down, up, down. You can go up, down, down, down. You can go up, up, down, down. Or you can go up, down, down, down. So there are five ways of doing it. And you know, oops. So let's do it again. Let's show that Mn, the set of n up and n down mountain ranges, is isomorphic to Pn, P open and P close, or n open and n close parentheses. And hopefully this is pretty obvious. I'll write the corresponding parentheses here. Open, open, close, close, open, close. And you can see it pretty immediately, a correspondence. Open, open, close, close, and then open, 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 close, close, close. You can see the correspondence. Every time you have an upwards mountain range, you do an open arrow. And when you have open parenthesis. And when you have a downward mountain range, you do a closed parentheses. That's another bijection, which I will call phi. That is a bijection between n by n parentheses and m up and down mountain ranges. So actually I said it's a bijection. We haven't shown that it's a bijection yet. So far it's just a function. But I've specified an arrow from here to here. No, I'm sorry. This is from parentheses to mountain ranges. So the arrow goes this way. All right. You see how everything in this set of things has an arrow going to up here to the set. Everything in the set of 5 open, 5 closed parentheses has an arrow going to the set of 5 up and 5 down mountain ranges. And if we reverse the arrows, there's a function that reverses all of the arrows. The arrows can point down, and if you do that, then the arrows point to the same place they pointed to before. By just saying that if you have an up mountain range, so let's see, when you're going from parentheses to mountains, you have an open parenthesis gives you an up mountain range, and a closed parenthesis gives you a down mountain range. And when you're going from mountains to parentheses, then it's the other way around. It's pretty straightforward. Then the up mountain range gives you an open parenthesis, and the down mountain range gives you a closed parenthesis. So we're able to reverse the arrows. So this function has an inverse from mn to pn, which means that phi is a bijection, and that means the number of things in Pn is equal to the number of things in Mn. And most importantly, n up, n down mountain ranges is isomorphic to n open, n closed parentheses. So cool. Now you're thinking like, wow, combinatorics is easy. Enumerative combinatorics is super fun. I like making bijections. It's really straightforward. Like, why, you know, I should become an enumerative combinatorist. Why not? So it sounds like you want a little more of a challenge then. So that's fine. Let's do something a little bit more challenging. We're going to study a new set now. So now let's study the set, what shall I name it? Rn. Okay. And this set will be... I've made a staircase, and now I'm going to tile that staircase with rectangles. Everything in this tiling will be a rectangle of some kind. Okay? Some are squares, that's okay as long as they're rectangles. So the question is, so let's see, I have 1, 2, 3, 4, 5, 6. I have 6 steps in my staircase. I have to use exactly 6 steps to tile my 6 rectangles to tile my staircase. So in this case, n equals 6, and I've tiled my staircase with 6 rectangles. The question is, how many ways are there to do it? So let's see, we're going to do this thing again. Okay, here's n. And we want to know what is the size of Rn given every n. So let's start with a 0 by 0 staircase. There it is. How many ways are there to tessellate it? I've already done it. So the answer is 1. Okay. Now we're going to start with a 1 by 1 staircase. Now I'm not drawing a picture or anything. This is actually just a box that is the staircase. How many ways is there to tessellate that with 1 rectangle? Done. Okay. It's really easy when you're first starting out with low numbers. So now we're going to have a 2 by 2 staircase. There are 2 ways to do it. You can do it like that, or you can do it like that. So, 2 ways to do it, like this and like that. Okay, so, wow, this is starting to look familiar. Let's see what 3 comes up with. I wonder if it's going to be 5. Okay, so we're going to have, okay, we're going to have like this, like that, like this, like this, and lastly, oops, like this. So there are 5 ways to do it. What do you know? What do you know? And spoiler alert. So, continuing along our previous pattern, our previous, fun that we were having, let's find a bijection between rectangle tilings of an n staircase. And what was the last thing we did? N by n up and n down mountain ranges. So, where is the bijection? This is not so straightforward as the last one was. Like, there's no obvious, open parentheses corresponds to up mountain. Like, you can't just look at this and see that anymore. So, this one's going to be a little bit more of a challenge. And if you are the sort of person who likes puzzles, then I recommend you pause the video now and stare at this for like 10 minutes or something and see if you can find the correspondence. See if you can find one that generalizes to any number n too, because I can just start, like, I can just start drawing lines, here, and yay, then I found a bijection. But what I'm interested in is what if n is an arbitrary number? We have to find a bijection that works for an arbitrary n, not just for when n is 5 or when n is 3 here. So, I can't just start drawing arrows here. Okay, so I'm going to assume now that if you want to tackle this one, you've already paused the video. We're back. So let's go over anyway my solution that I made. And the key is, with mountain ranges, is you have some mountain range, okay, and it may go down and touch the horizon at some point, and then it'll go back up, it might touch the horizon again, and then, okay. Every mountain range, after its initial position, touches the horizon at least once. It may wait all the way until the end before it touches again, but it will have a first time that it touches the horizon again after it starts. So the key here is to use that as a bisection point and partition this mountain range into two parts. There's this part that happens before the first touch, and then there's another part over here that happens after the first touch. Okay? Now I'm going to, when I look at my tilings of an end staircase, I'm going to look at the tiling that touches the lower left corner. Whichever tiling touches this spot right here. Okay? And that is going to whichever one that is going to correspond to this middle point. This is my trick. This is a trick that I'm using to make this bijection. Anything above, so then I have this rectangle that contains this lower left point. Anything above this rectangle, I'm going to dump here to the left of my bisection point. And anything to the right, for example, if I have a bunch of stuff over here to the right, all of this stuff, I'm going to dump to the right of my bisection point. And then I'm going to do a recursive algorithm. So let's run an example. I'll come over here. I'll run an example from this sixth staircase, 1, 2, 3, 4, 5, 6, yeah, to a 6 up, 6 down mountain range, and we'll see how that goes. Okay, so I'm going to cut it in half, and I'm going to mark this point right here, and then this is the rectangle that is that is touching my lower left point. So it is going to correspond to that point right there in the middle. Okay. Now, I guess I forgot to mention something. I drew a little raised horizon line here. That's necessary. That's necessary. Because because this is the first time that it touches, this right here is the first time that it touches the horizon on the left of my middle point line. So you know that the mountain range never comes and touches the horizon again. That never happens. So I'm going to draw a new horizon line that's one level up. Now this horizon line might get touched. There's no guarantee there. Maybe, maybe not. But we know that nothing's going to happen below that. So I'm going to draw a corresponding thing. If you don't see why, hold on. You'll see in a second. I'm going to draw a corresponding mountain over here with a raised horizon line, and then everything above this middle block, I'm going to dump on top of this raised horizon. And everything to the right, I'm going to dump below in this valley. Okay? So let's do that. Let's do that. Let's see. So everything up here, and then I'm developing this recursively. So now I'm only going to focus on what's happening in here, and I'm going to have a new point right there. Okay, and I'm going to bisect it again. Let's find a new color here. I'm going to bisect it again, and then this point is going to correspond to that middle point. I'm going to draw a new raised horizon. And anything above this block is going to go in the raised horizon. But there's nothing above this block. So there's nothing, oh my god, undo. So there's nothing in my raised horizon. My raised horizon is empty. So I'm just going to draw it like that. Okay? But we do have something to the right of my raised horizon. I'm sorry, to the right of this block. So we're going to bring that over here, and we're going to draw a mountain in my raised block. Let's use a different color, shall we? This color. We're going to draw a mountain in this raised block, in the lower part. Not in the raised part, in the lower part. Okay, so now we finished recursing on the top side. Let's do the recursion on the right side. So I'm going to pick this lower left point, and here's the corresponding block. I'm going to cut the lower side in 2. Now anything to the above of this purple block goes in the raised portion. Here's the raised portion right here. But there's nothing above here. There's nothing here. So that means that the raised portion is empty. So I'm just gonna draw an empty raised portion there. And now everything else is going to go to the right of this line, because everything else is to the right of the purple block. Hopefully all the repetition here is causing this to make sense. So now I have a new block. I'm gonna cut this guy in half. I'm gonna draw a raised portion here. Okay, now I look, everything above the blue block goes in the raised portion. And so there's going to be one block in the raised portion. This block corresponds to that. Whereas there's nothing to the right of the blue block, so actually this just goes away. Okay? So wow, that was kind of weird and complicated. Let me draw the finished one. Let me draw the finished, and I'll even do it preserving the colors. Go up, and then we go up, down, and we switch to orange. We go up, down again, and then back to blue. We go down, and then purple, up, down, and then dark blue, up, up, down, down. This is the mountain range, and up and down mountain range, that corresponds to this 6-step rectangle tiling. So the question is, let's see, well, which way did we do? We did this way. We did this way. We started with the rectangle tiling, and we got an up and down mountain range. So that is a function phi that goes from rectangle tilings of n tilings to mountain up and n down mountain ranges. So can we reverse the arrow? Can we start from mountain ranges and go to rectangle tilings? That's the question. And yeah, we use the same trick we did down here. We find the first time that the mountain range touches the ground. It's right here. And we correspond that to, we basically reverse the process that we just did. It's not as trivial to reverse this process as it was to reverse the other bijections that we found. But it's still possible. We find the first time that the mountain has touched the horizon. We make a raised portion of everything to the left. You see that nothing ever will go below that raised portion. And then you recurse. So everything here will end up there. And everything to the right of it, below in the valley, so to speak, will end up over there. So to put that another way, when I cut it at the point where the mountain first touches the horizon, everything above this mountain will end up above this block. And everything below the mountain to the right will end up to the right of this block. And you can see that's true because there are 1, 2, 3 upper slopes to the right of this cut, and there are 1, 2, 3 blocks to the right of the cut. And there are 1, 2 upper slopes, not counting the raised portion, to the left of this block, and there are 1, 2 upper slopes above, there are 1, 2 rectangles above this middle block. Okay, hopefully that made sense. This one's kind of tricky to visualize. If it didn't make sense, watch it again or try to build this bijection yourself. It's a little bit of a challenge, but it's going to get easier from here on out. the point is that we've got this bijection from Rn to Mn, and we've also found a way to invert it and go from the mountains to the rectangles. And so we've shown that that these two sets are isomorphic, and correspondingly that the number of tilings, rectangle tilings, is the same as the number of mountains. Pretty cool. Pretty cool. Okay, so let's move right along here. The next bijection we're going to find hopefully is a little bit more straightforward, since we've already found a similar bijection. And we are going to look at triangulations of an n+2-gon. Okay, an n+2 sided polygon. So I'm going to draw a hexagon here. A hexagon is 6-sided, so n is 4. 4 plus 2 is 6. And we're going to look at the number of ways that you can triangulate a hexagon. So here's one way, right? Here's another way. These are all triangles now. Here's another way. Now these have to be different, like different rotations are considered different triangulations. So here, draw that better, is another way, and then here's another way. All right, so hopefully that gives you some idea of what's going on here. So let's start back with n equals 0. Let's skip n equals 0. N equals 0 is boring. I think I've pretty much gotten you with that trick. Okay, so let's start with n equals 1, and we want to know how many triangulations there are. How many triangulations of an n+2 polygon? If n is 1, then we just have a triangle. So it's already triangulated, we're done. If that was n equals 1. N equals 2, we have 2 plus 4 is a square. Our polygon has 4 sides. And we have 2 ways of doing it. We can triangulate it like that, or we can triangulate it like that. So there are 2 ways of doing it. Let's look at n equals 3. This is a pentagon. A little bit harder to draw, but I'm going to try and draw enough of them. Pardon my very bad art here. All right, and then these are the ways to do it. Yeah. So when there are 3, so when n is 3 and we're triangulating pentagons, there are 5 ways to triangulate pentagons. Spoiler alert. You know, if you didn't guess that, then, you know, I can't help you. Okay, so this looks like it's the same number as the other stuff. Let's try and find a bijection. A bijection between, what was the last thing we did? A bijection between rectangle tilings. So we want to find phi, a bijection between triangulations and rectangle tilings. That's what we're going to try and find. Okay. And I'm going to start again. I'm going to start fresh over here. So here we go. Let me draw a very large polygon. Okay, it's going to have plenty of sides here so that I can describe the algorithm. This one's going to be a little bit easier to see, and hopefully it will provide some clarity to the last algorithm, which I'm not sure I explained very well. Sorry about that, but it is what it is. I'm going to try, oh my god, can I get a straight line here? There you go. Okay, and I guess I'll do it here and something like this. I don't know. There. And then, so there are 8 sides here, so n equals 6. So now I'm going to draw 2, 3, 4, 5, 6. All right. And so I have to find a tiling, a rectangle tiling of this with 6 rectangles that's somehow equivalent to this guy over here. So the first trick is to fix one of the edges of this octagon. Because remember, these tilings are not the same if you rotate them. Like this tiling and this tiling are considered, and this tiling are considered different tilings, right? So if I fix one of the edges, let's use this edge right here. I'm going to fix this edge. I'm going to make it a special edge. So if you rotate it, it becomes a different tiling no matter what. Okay? And I'm going to use that as my starting point. Same way I did before, there's going to be a corresponding rectangle somewhere in this area. And that rectangle will correspond to this triangle. Okay? Now, if you see that, if you think of this side as the underside of the triangle, then this triangle has a left and a right triangle that also touch it in this triangulation. Okay? And we can see that on the left, there are a total of 3 other triangles. And on the right, there are a total of 2 other triangles. So I'm going to draw a box over here that has 3 steps above it and 2 steps to the right of it. So my correspondence here is that to the left of this triangle is like up, left is like up, and then right is like right. Okay, so let's try and draw this box. There should be 3 things above it because there are 3 triangles to the left of this triangle, and there are 2 steps to the right because there are 2 triangles to the right of this triangle. So there it is. There's my box. This box corresponds to that white triangle. So let's do it again. We're going to do this recursively, and the way we're going to recurse is by considering the edge of the new triangle that touches the old triangle, which I'm drawing here in green, okay? That is our base edge. So now we kind of have to turn our heads sideways here. This is our new triangle, and it's going to have a left edge and a right edge. And we can see that there are no triangles remaining out of the left edge. There's nothing else there. But there's one triangle remaining out of the right edge. So I have to divide the remaining space right here so that there's one triangle step to the right and no steps above, and this is the only way to do it. Okay? So that green triangle corresponds to this green block, and the only triangle that's left over here corresponds to the only block that's left over there. Now let's do it with the other triangles and the other steps. I'm going to color this triangle in yellow. Alright. And the base of the yellow triangle is the side that touched the old white triangle. So it has a left side and a right side. And there is one triangle each on left and right. So I have to divide this remaining space up here in a way that gives me one box on the top and one box on the bottom. There's only one way to do that. There it is. So this yellow rectangle corresponds to that yellow triangle. And then we have the 2 remaining triangles over here. This one's on the left, so it corresponds to up. And this one's on the right. I'm sorry, yes, the right. And so it corresponds to right. And so now we have our function. We still have to show that we can reverse the triangle, though. We still have to be able to start here and go back the other way. And that I'm going to leave to you as an exercise. It's very fun. Just start with a n stair step and build a corresponding triangulation of an n+2 polygon in a way that will always get you back the same n+2 polygon as the one that I started out with here that you that you start out with when you do this algorithm. So if you do that, then you have a function phi. We did this one. We found triangulations to rectangular tilings. And then your homework is to make a function phi inverse that does the other way around, that reverses all of the arrows. And once you have that, you will know that, that these two sets are isomorphic. And the number of 1000 by 1000 triangulations of a 1000 two-sided polygon is the same number as the number of ways to tile a 1000 step staircase with 1000 rectangles. Same number of ways. It doesn't matter what n is, it could be 1,000,000. It's going to be the same number of ways. So hopefully that one was a little bit more straightforward and easy to understand, this bijection, than the original one. Those mountains are kind of weird to work with. So let's keep charging ahead here. It only gets more fun from here on out, folks. If you've kept up with us until this point, you're in for a real treat, because we're going to start doing some really cool stuff. Let's get a new set, Bn, of binary trees on n vertices. Okay? So let's do this. Binary trees on n vertices. How many ways are there to do it? If you have one vertex, here it is. There's only one binary tree on one vertex. Now, if you have two verts, a binary tree has to have a root. It has to have the root of the tree. And so you can either have a root and a left child, or you can have a root and a right child. This is how this is going to work. So there's two ways to do it if you have two verts. Okay? Now, what if you have three children? I'm sorry, what if you have three verts? That means you have two children. So you can either put both verts going to the left, or you can go to the left once and then to the right, or you can go to the right once and then to the left, or you can go to the right and then to the right, or you can put one to the left and one to the right. So there are 5 ways of doing this. And of course, probably see the pattern. Okay. So let's show that this is in bijection to the number of triangulations of an n+2 polygon. And this is one of the coolest and easiest bijections to see. I'm going to draw another n+2 polygon. Okay, I'm going to do n equals 6 because I have this fun way of drawing octagons. This way, this time, I have to fix a side. And instead of fixing the bottom side, I'm going to fix the top side instead. Okay? So let's fix this top side right here. And then my rule is I'm going to start drawing the binary tree right here. This is my root node. These were my root nodes before. Okay? But here I'm going to draw my root node right here on my special side. And then you see that other than the special side of the triangle, I have 2 sides in every triangle, right? There are 3 sides total. I take out the special side. There are 2 remaining sides. I'm going to designate one of those as the left side and one of them as the right side. And here's the trick. If the side in question is an internal side in my triangulation, then it gets a child node in my binary tree. Okay? And then that new side becomes a new node, and it has a left and a right. And so we can draw some children like this. Now once we get to here, we see that all the remaining sides are external edges of the binary tree, so we stop. We don't draw any new children there. Over here on the right, we have a right side and a left side, But unfortunately, this right side right here is an external edge of the tree, so we don't give him a node. There's no node there. But there is a node here. And then these two are both external, so they don't get nodes. So reforming this binary tree, you can see it looks like this. Okay, remember this is a left child because we're coming to the left side of the triangle. So this is really cool. To go from triangulations, this is T6, and this is B6. To go from triangulations to binary tree, you can just draw the binary tree right on top of the triangulation. It's really cool. And to go the other way around, I mean, I hope it's obvious that to go the other way around is pretty straightforward. You have a binary tree, you kind of morph it into this shape, you pretty much draw a polygon on top of it such that none of the, okay, let me do it right here. Let me draw a polygon. So this is my special side. It's going to look warped. It won't look like a regular octagon like I did before. In fact, I might have to do like, I might have to do like this, okay? But I'll work that out later. Oh no, that's not the way it looks. Okay, let's do this. Here's a little triangle right here, okay? And then here is another triangle right here. And there's a triangle, and there's a triangle. Again, I'm gonna have to fix this up later. So let's see, did I do that right? No, I need one more triangle right there. There. Now, with the exception of the root node, all of the other nodes in my tree are internal. And if I just morph this guy back, you can see that it's really the same. Like, I'll draw in some colors here. This guy corresponds with that guy. And then to his left, he's going to have a green triangle that corresponds with this green triangle. But to his right, he's going to have a purple triangle that... You see there's the same structure in these two. You just have to kind of morph it back so that it fits into an octagon. So there's my bijection. So we've shown that Tn has the same size as Bn. We did it with 6. We did it with n equals 6, but I hopefully it's pretty clear. I hope that it's clear that this will work with any value of n. Because we didn't use the number 6 anywhere in our proof, right? So it'll work with any number. So the number of binary trees with 1,000 nodes is the same as the number of ways to triangulate a 1,002-sided polygon. That's pretty cool. We're going to do one more bijection here. And because I've run out of letters, I'm going to use D. Okay. And D is the number of rooted trees on n plus 1 polygons. Rooted trees on n plus 1 polygons. And I'll show you what a rooted tree is. Okay. This is a tree. It's no longer a binary tree because children are now allowed to have nodes are allowed to have more than one children. But it's rooted in that one of these nodes, one of the vertexes of the tree is specified as the root of the tree. So the question is, how many rooted trees are there on n plus 1 vertices? So let's see. Dn, size of Dn. So when n equals 1, we have two verts in our tree. All right, this is it. This is all we can have. See, this time it doesn't matter whether it's left and right. It's just a child. So this is the only solution there. So it's 1. So next, let's do 2 children. Okay, I'm sorry. N equals 2. So we have 2. So we have 3 nodes in our tree, and we can do this. We can do like that, where this is the root. Sorry, I should have said this is the root. Or we can do like that. I'm going to consider like this to be the same at like we make no distinction among children anymore. There's no left and right. So there's really only one way to do this. We hang this guy off and we hang that guy off. So there are exactly two solutions here. So now let's look at 3. And here's our root node. We can hang guys off like this. We can hang guys off like this. Here's the root. We can hang guys off like this. And like that. And then finally we can make all 3 children. So there are 5 ways to do it. I don't think I forgot any. You know. All right. So let's find the last bijection. This is the last one. We're going to find a bijection between rooted trees on n+1 nodes and binary trees on n nodes. So this is actually kind of surprising because we started with a binary tree, we added 1 node, but then we took away the restriction of having only 2 children. And so somehow those 2 operations ended up being the same thing, and you still have the same number of trees. So the number of trees, it doesn't matter how many nodes there are. Like I could keep, I'm sorry, how many children there are. I could keep adding children here. Doesn't matter. If you fix the number of nodes plus 1, it ends up being the same number of binary trees. That's interesting. So let's find out how. Let's form this bijection. And to do it, I'm going to come up with a very complicated tree. And we're going to do the bijection on a very complicated tree here. Okay. There. Is that complicated enough? We're going to find the binary tree that corresponds to this guy. Let's see. Is that? Yeah, that stands out. So the first thing to remember is that the rooted tree has a designated root. But the rooted tree is on n+1 vertices, whereas the binary tree is only on n vertices. So we have to get rid of one of these vertices. So we're going to get rid of the root. The root is not going to be in our binary tree. Then we're going to start the binary tree with the root of the binary tree being the first child of the root node. Here's the first child going from left to right. That's going to be our root node of the binary tree. Then anytime here's the rule. Anytime a node has a first child, that becomes the left child in the binary tree. First child in the rooted tree becomes the left child in the binary tree. And the next sibling becomes the right child in the binary tree. Okay? So let me continue with that algorithm here. We've got no first child here, so we've got no left child in the binary tree. But we do have a next sibling in the rooted tree, and he becomes the right child in the binary tree. Now we have a next sibling in the rooted tree, so that becomes the right child of this node, and we have a first child in the rooted tree, which becomes the left child in the binary tree. And then we have no first child here, but we do have a next sibling, which becomes the right child, and then another next sibling, which becomes the right child. These guys have no left childs. Okay? This guy has no left child because he has no first child, and he has no right child because he has no next sibling. This guy has a first sibling, which becomes the first child. I'm sorry, the left child. And he has a next sibling, which becomes the right child. He has no first sibling, so he has no left child, and he has one next sibling, so he has a right child. Okay, let's go a little bit faster. That's a left child. That's a right child, no left child here. That's a right child, a left child, and then a right child, no left child here. No children here. No children. So remember, this was the root, so I'm going to draw the resulting binary tree on the left. On the right over here. So we go like this, and then over here we take a right, and we go down like this, and we go down like this. And then over here on the right, we have a little offshoot right here. And then we go off to the right, and we do this. And then we come out like this. There we go. This is the binary tree that corresponds to this rooted tree. So the rooted tree had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 verts. So n equals 16 here. And we should have 16, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. We have 16 verts in our binary tree. So this is kind of interesting. There is a binary tree hidden inside every other tree if you assign a root. And let's bring it back to programming here now at the end of this talk, because we're probably mostly programmers. Let's say you have a folder, like a file folder system. And every folder can have a bunch of child folders, right? So like you have your My Documents folder, and inside your My Documents it has cat pictures and dog pictures, and inside cat pictures it has black cat pictures and white cat pictures and blue cat pictures and so on, right? A file system. You all know what that is. Hopefully you've used a file system before. If we want to represent this file system, I'm going to make struct f be a struct that represents a folder, okay? And then we have to have a vector of other f's, well, pointers to f's, for subfolders. That's kind of messy because not only do you have to allocate all of these other f's, but you have to allocate space for the vector too, which is a list of pointers. So instead of doing it that way, we can do it this way instead. So we still have to allocate all of the f pointers, all of the f structs for our folders, but we no longer have to bother with this vector. So that reduces the amount of memory allocations that we have to make a great deal. And we can do this because a rooted tree on n plus 1 vertices is isomorphic to a binary tree on n vertices. So that brings me to, why on earth did I do all of this? Like, normally the stuff that I do is much more applicable to programming and video game development in particular, and this time I kind of went off on left field with this whole deal about bijections and enumerative combinatorics. And the reason is that I wanted to illustrate a different way of thinking about things. When you can make an isomorphism between two sets, like I've done here, I've made an isomorphism between binary trees and rooted trees, then that means those two things have a similar structure. Internally, structurally, they are the same. They're not the same things, just because if two sets are isomorphic doesn't mean that they're the same thing, but it means that they share some kind of structure that means that you can do with one of them the same thing that you can do with the other. They are functionally equivalent. They're not the same thing, but they're functionally equivalent, right? So that means that if you have trouble reasoning about one of these sets, you can transform it into the other set and you can reason about that set instead, it might be easier to reason about the other set. For example, behavior trees and state machines and processors, programming languages, any programming language really, these things are all Turing complete, right? Any Turing complete language is isomorphic to any other Turing complete language. But that doesn't mean that you can do in one language anything that you can do in another language. Some languages are easier to solve some tasks than other languages are. And so that means that if you pick the best tool for the job, then you can solve the problem with the most appropriate tools at hand instead of. So, for example, I initially said behavioral trees and state machines. They might be isomorphic; they're both Turing complete, but behavior trees are better for artificial intelligence, whereas state machines are better for. I don't know. State machines are good for a lot of things, like describing the internals of a processor. Right, describing the behavior of logic circuits, for example. You wouldn't want to describe logic circuits with a behavior tree, and it's clumsy to specify the behavior of like an enemy in a video game with a state machine. It's much easier to use a behavior tree. So by identifying these things that are isomorphic, you can have better tools for thinking about, for approaching the problems that you need to solve. So I hope that this very long video is interesting. That brings us to about the end here. If you like, try looking up things that can be enumerated by Catalan numbers. And it's a fun game to try and find these bijections between things. I had a lot of fun putting this together and finding a lot of these bijections. In fact, I left a few of them out. Here's some more homework for you. Okay? I'm going to leave you with some quick homework before we go. There's 6 people standing in this circle, and they want to shake hands. But the rule is, if these 2 people shake hands, then nobody else can cross shaking hands. Okay? Like since these 2 people are shaking hands, nobody over here can shake hands with anybody over there. So this is non-crossing handshakes between 2 n people. Okay, here n equals 3. You have 2 n people, and now the only other way to do this is this right here. All right, so if I add a few more, I'll add a few more. I'll make n equals 6, and we'll draw 12 dots. And then I will draw another valid solution here. So I'm going to have these 2 people shake hands, and then these 2 people and these 2 people. So this right here is a valid solution. Notice that no hands are crossing. This can also be enumerated by the Catalan numbers. And there's a nice puzzle for you. Find a bijection between this and any other of the sets that we just did. I had a lot of fun doing this, and I hope we learned some things about isomorphisms. The word isomorphic is very powerful. You can say 2 things are isomorphic. I hope to hear people using that one a lot more, because it's a great word. So great. We're gonna skip next week, and then we'll be back the week after with some more numerical analysis. See you then.